Hello, and welcome to BitBusters. I'm Mark Jordan.
And I'm Sylvia Hooks. Today we're exploring 802.11ac, the new wireless standard that delivers gigabit speed Wi-Fi, connects more devices in high-density environments, and provides explicit beamforming to improve throughput and range.
That's right, Sylvia. But a lot of people don't know that one of the biggest advantages of 802.11ac is what it can do for 11n clients. It actually makes 802.11n clients go 3 times faster. We'll show you the details about that later, but first, let's take a look at the fundamental differences in 802.11ac architectures.
A lot of enterprise organizations have already started deploying AC, and today they can choose from 2 types of access points, purpose-built and modular. We're going to compare both, the purpose-built AP225 from Aruba and the modular AP3600 from Cisco.
The physical components inside a purpose-built AP versus a modular AP are always different. The Wi-Fi chipset, the processor, the memory, even the antenna. This has a tremendous effect on performance, specifically throughput and range. Let's have a look, Sylvia.
Okay, this is Aruba's 802.11ac access point, the purpose-built AP225. It's designed from the ground up to be an AC access point. This one's got a Broadcom BCM43460 Wi-Fi chipset, a Freescale P1020 processor with 2 active 800 MHz cores, and 512 megabytes of RAM, plus 6 optimally placed integrated down-tilt omnidirectional antennas for 3x3 MIMO.
And this is Cisco's 802.11ac AP, the modular AP3600. And here's where the problem lies with modular APs. This one was designed 2 years ago with the best possible parts at that time. It was a good 11n AP, but now it has to accommodate a Snap-on 11ac module. Let's look at the Snap-on module, since that's where the new 11ac components are.
The Cisco AP has a Broadcom BCM43460 Wi-Fi chipset, same as Aruba, but only 256 megabytes of RAM and a Freescale P1023 dual-core processor that cycles at 800 megahertz, but with only 1 active core. The processor and memory are important. Wi-Fi environments are getting more crowded due to the big influx of mobile devices. Processor performance is critical in high-density climates. The extra memory speeds up all the functions on the AP and enables it to multitask.
Then there's the antenna design and layout, which is critical to improving range and throughput at range. The Cisco AP has 3 integrated planar inverted F antennas, the kind you'd find in an 11n AP. There are actually 4 antennas, but only 3 are connected for 3-stream MIMO.
And unfortunately, you can see here that the antennas are not optimally situated. This is the way it is with every modular AP. Because the module's real estate is limited, you have to make antenna design compromises. So unlike a purpose-built AP, you'll never be able to take advantage of the AP's entire surface area.
That's right. Okay, I think it's time to prove that these numbers actually mean something in a real-world performance test using 802.11n and AC devices.
We shot this test at my happy place, the Proof of Concept Lab. Let's check it out.
We installed the Aruba access point and the Cisco access point in the exact same location. And then we wirelessly connected an 11n capable MacBook Pro, followed by an 11ac capable MacBook Air to each access point. Then we started a continuous file download to measure the maximum throughput.
And since this is a real-world test, and in the real world people move, we've chosen our preferred method of office mobility. We attach each laptop to a radio-controlled helicopter, which will carry them away at various distances from the 11ac access point. So, let's get airborne.
Yeah, this is really cool. All right, let's take a look at the results of this. At 75 feet from the Aruba access point, the 11n 3-stream download rate was 186 megabits per second, and the 11ac 2-stream download rate was 402 megabits per second. For Cisco, the 11N 3-stream download rate was only 76 megabits per second, and the 11AC 2-stream download rate was a low 174 megabits per second. But at the farthest distance, 120 feet, the Cisco access point dropped like a rock to only 5 megabits per second for the 11N device and 39 megabits per second for the 11AC device. Aruba maintained a throughput rate of 128 megabits per second for the 11N device and 202 megabits per second for the 11AC device.
Well, Mark, I think that test proves our point.
That's right. Despite 802.11ac being the standard, not all implementations are the same.
And the design has everything to do with it. Not just the inside, but the outside, because there's an extra module. Just look at the difference between the modular and purpose-built APs.
Yeah, this one's pretty heavy. Imagine installing 100 of these bad boys in a day. Let's get real and weigh these guys. The Aruba access point comes in at 1 pound 7 ounces, while the Cisco access point is 3.5 pounds, double the weight of Aruba.
Double the weight. Double the weight and you double the damage, right, Mark?
I suppose that's true.
Okay, Mark, I have a great idea on how to show this. This is the AP drop test rig that we're going to use to see how much damage gets done.
And to make this fun, we're going to drop both APs from the same height onto a pane of glass. Let's drop the lighter Aruba AP first. And 3, 2, 1.
Wow, so no damage whatsoever at all on the Aruba AP.
Yeah.
But I think it would still hurt if it fell from the ceiling onto my head on the way to the break room.
I'll bet you're right about that. Okay, let's see what happens with the heavier Cisco AP. Ready? And 3, 2, 1.
Well, Mark, once again I think we've made our point. Design matters.
I couldn't agree more, Sylvia. And so does price. Modular APs deliver only 1/3 of the performance, weigh twice as much, and cost 50% more. When it comes to a purpose-built versus modular approach, the answer is a no-brainer.
That's it for today. Join us next time when we bust some bits for controllerless Wi-Fi.
See you then.